All right, welcome to the podcast on integrated rate law. This is the second podcast of Kinetics and the third set of notes. And integrated rate law is when we monitor the change of a reaction over time. And the word integrated comes from integral, and again, those of you in calculus know all about that and finding the area under a curve and stuff like that. And those of you not in calculus don't have to worry about any of it. But what we're going to do is we're going to see how these changes over time can be plotted and how we can calculate maybe an initial concentration or a final concentration based on the data we're given. And like before, we will only work with zero order, first order, and second order. Now, again, I had mentioned in the last podcast that you can have other orders in that. We can have fractions of orders and so on, but the AP course tends to stick with 0, 1, and 2. So that's what we're really going to focus on. So let's move on to our first order integrated rate law stuff. And I've got a reaction right here. Maybe. Again, I'm having difficulty with... Okay, so here's first order. So here's a reaction. Now let me move my arrow. Got an arrow here. Let's put it right there. So there's dinitrogen pentoxide breaking up into nitrogen dioxide and oxygen. Okay, and the rate has already been found to be first order. You can see right there that it is a first order reaction. So what happens in this situation when the concentration doubles, the rate doubles. So you can imagine instead of having a 1 molar concentration, we have a 2 molar concentration. And if we have twice as many moles, the reaction rate would increase. And so if we look at this, we have this new thing called the integrated rate law. And this equation, by the way, does happen to be on your AP equation sheet. And what it is if you take the natural log of the concentration of dinitrogen pentoxide, that equals the negative K. Now, that K is still a constant that we used last time. T is time, because now we have this new variable. We're plotting this over time. And plus the natural log of whatever this concentration was at the start. This is 0, which is not, and that just means at the start. And ln is natural log, and we have that key on our calculator, and so we can go from there. Now, if we were to look at a plot of the possible ways we plot this thing, well, that was a poor sentence, but anyways, if we look at possible plots, we get these 3 graphs that I have right here. So we get this curve if you plot the concentration versus time. We get a straight line if you plot the natural log of the concentration versus time. And we get a curve going up if you plot 1 over the concentration versus time. Now, if you notice, a straight line's good, right? I mean, finding the slope for a straight line is much easier than trying to find the slope of a curved line. And so if we look at the way the rate law is written up here, okay, what does that look like from your math classes? Well, yeah, it looks just like a straight line equation, right? Y equals ms plus b. And so you can see that y equals the natural log of the concentration. M is our K, X is our time, B is our initial concentration. And so if you guys know that M means the slope, if you can find the slope of one of these reactions, you can find the constant, which makes it very handy, especially if you're using a graphing calculator or a program that will do that for you. But what's important to note is that the kind of questions that you see in AP courses is that they'll show you these plots and they'll ask you what kind of order or what order is this reaction. And so in your brain, what you've got to do is you've got to get this part memorized. If you ever plot the natural log versus time and you get a straight line, like we have right there, that is always first order. And I can't tell you how often that question comes up. So it's something you have to commit to memory. All right? A natural log of the concentration versus time, if you get a straight line, you have a first order. And it's something to note also that this negative sign right here, that usually takes care of the fact that a first order plot is going to have a negative slope, right? So let's look at the kind of problems we might see from this. Oops. And so again, it's the same kind of reaction right here. And so they've given us some data, and they tell us that it's first order, which means we can use this expression right here. And if I haven't mentioned it already, there's a variation of this equation for each order, 0, first, and second. So what they want to know is what is the concentration of our reactant at 700 seconds. So the nice thing about this is it's just kind of a plug it in kind of thing. All right. So what we're going to do is we're going to take the numbers they give us. Now they told us that K equals 8.03 times 10 to the negative fourth seconds plus, oops, let me pause this or let me erase that for a second. I'm forgetting my time component. Okay, different color. Times the time, which happens to be 700 seconds. All right, I had a slight little brain fart there. Anyway, so I put in the log of 1 because you can see right over here that the concentration at time 0 is 1.0. All right, so then we're just going to go ahead and solve for this. Negative, and those two times together gives me 5.621 plus, now the natural log of 1 happens to be 0. So then what I want to do is I want to take the antilog, which on your calculator is the e to the x key. So if I, in my calculator, put a negative 5.621 and hit e to the x, I get a value of 0.0036, and that's of course in moles per liter, and that is the concentration of A. Okay, so at that point, at 700 seconds, we would get that concentration. And that's basically how you're going to do these problems. You're going to use that integrated rate law expression there, and just move on from that one to the next one. Okay, so let's try another one. Okay, so we've got some more concentrations. We've got some more time, and look what this says. Calculate the rate constant for the first order reaction using the values in the table. Include the units in your answer. So again, we've got this expression, and actually, let's see, how would I want to do that? Alright, so there's the formula to use for this just to make this easy. So let's do this first problem right here. We know it's first order, so I can use this expression right here. And of course they want the units. And I'm just going to pick some numbers here. So I'm going to pick, I'll pick these two numbers right here. So the natural log of 3.00 times 10 to the negative fifth equals K. Actually negative K, so I forget that. And that was at 44.2 minutes. Alright. Plus the natural log of 1.20 times 10 to the minus fourth. Alright. And so natural log of that gives me negative 10.41 equals negative K. Actually, it gives me negative 44.2 K plus a negative 9.028. And so then when I solve for K, I get K equals 0.0313. And look at the time. The time was in minutes. So instead of it being per second, this is actually per minute. So now I've solved for K and I've included the units. And again, if you recall, first order K values are in some unit per time, right? So let's look at the second question here, where it says calculate the time it takes for the concentration to go from that to that. So here's my, right here is my initial concentration, or the knot, and then this is the other one. So now what we're going to do is we're going to solve for T, and since we have a value for K, it shouldn't be too tough. So I'm going to go natural log of 1.50 times 10 to the minus fifth, and that equals negative. The k that we had before was 0.0313 times t plus the natural log of 1.20 times 10 to the fourth. Okay, and so then I use my natural log key. I get negative 11.11 equals, this is negative 0.0313 t's plus negative 9.028. And if you solve for t, you get t equals 68.6 minutes. So there we go. We've used the first order integrated rate law to do a couple problems, which again you're going to need to do in order to solve some of the problems they're going to ask you on the AP test. So let's move on to second order. Now second order, there's a whole new set of graphs, and if you recall, a second order rate law. Whoa, I can see I've got a typo right here. Second order rate law. Alright, technical difficulties here. Somehow I went to the zero order rate law. So there we have our expression right there. The rate law equals the concentration over time, which equals second order. Okay. Now the integrated rate law for this one is, again, it's the same concept. Y equals mx plus b, right? So instead of plotting the natural log, we're going to plot 1 over. And so these are the only two parts that change, except that you'll notice there's no negative sign here. And let's look at our graphs to see why. So if I plot the concentration versus time, I get a curved slope. Same thing with the natural log. But if I plot 1 over the concentration, I get a slope. And notice it is a positive slope. So in our expression, you're not going to see a negative right there. Right? So the second order one is the positive one. And so again, something to remember, something to memorize. If it's a straight line versus 1 over the concentration, it's second order. And the questions can sometimes be as simple as, here's 3 graphs, what order will it be? And you'll just look for the straight line. And if you have that second order is the 1 over the concentration versus the natural log, or when we get to zero order, just the concentration, then the problems will be pretty trivial to you. So let's do a problem. I think I have a problem here. Okay, here we go. Oops, let me fix my arrows. Boy, I thought I had this all typed in. Alright. Alright, so I've got this equation up there. So let's just start plugging in the numbers for this second order problem. I've got 1 over 0.25, right? Because you can see that's my final concentration, equals the K, which I'm finding, times the time, and it says 25 minutes, plus 1 over, the original concentration is 1 molar, right? So this is where, by the way, you'll find your 1 over x key on your calculator. That's where it kind of comes in a little handy. So 1 over that equals 4 equals 25 k's plus 1, and so we get a value for k to be 0.12, and then the unit is liters / moles minutes. Now, if you have that memorized, that unit for a second order, that's great. If not, if you think about it, we've got concentration on the bottom, a reciprocal of concentration, so that causes those two to flip. All right, so there's one problem. Again, if you think you can do these problems without waiting for me, knock yourself out, pause the video, and do it. So I'll do the same thing with this next one, because this one's just a little tricky. We've got some acetaldehyde, we've got a constant, we've got a temperature, 80%. Okay, so let's start plugging in these numbers. 1 over the original concentration. Now this is where it's just a slight little glitch or little bump. We've got this to start out with, this 0.0750 molar. And this says how much time would it take for 80% of the aldehyde. So what's our concentration when 80% of the aldehyde is gone? Well, hopefully you're going, well, it would be 20%, right, of that number right there. So find 20% of 0.750, which comes out to be 0.0015, and that equals their constant 334 moles per liter seconds. And you can see from where I got the problem how they just put molarity. Whoa, let me flip things over. As I just said, try that again. Liters, mole, there we go. All right. And then we're solving for T, and plus 1 over the 0.0075. All right. And then this number comes out to be, well, you know what? I don't have it written out, so I'm just going to do this. I'm going to put, when I work this out, and since you guys are all really good at math, I get 1,597 seconds. So give that a shot. Hopefully you got the same answer. If not, definitely ask me about it tomorrow. All right? All right, so last but not least, let's look at what a zero order reaction looks like. And there's our zero order. And so again, same kind of integrated rate law expression, except this is now the concentration, negative KT. And you can see the reason it's negative. If you look here, here's the slope when you plot the concentration. It is a negative slope. All right. So again, this is the thing you have to remember. Which order goes with which plot? Because that is a question that pops up all the time. Now, zero order rate law expressions are kind of weird because if you look up here, basically the rate law is just due to the constant. And that tells you that it doesn't matter what the concentration of this reaction is going to be, it's going to go at the same rate, essentially. And that, if you look down here, that happens mostly on the surface of something like when you have a catalyst involved, or apparently with enzyme chemistry. And I'm not a lot really familiar with that, but anyways, so now instead of doing a problem with that, we're going to go ahead and move on just to a quick summary. And I just want to show you this page right out of your book. This is not a bad piece of information to get on a piece of paper, and just because it kind of does a really nice summary of all the reactions. You can see what their rate law is, which you already know. Now you can see the integrated rate law, and then what it takes to get a straight line, and the slopes and so on. And then this last thing, which is what we're going to finish up with, is the half-life. And you can probably imagine what half-life means just by the term half-life. But we're going to go ahead and look at how we can do some problems with it. Okay, so as I've got right here, the half-life is how much time it takes to reach half of the original concentration. And it's pretty straightforward for one of the reactions, and the other one you have to kind of think about it. So basically, if you look at this, the half-life means the concentration when the concentration is in half. And that is the time it takes for half the concentration to go down. So for a first order reaction, you get the natural log of 2 equals the constant times whatever the time is, right? And if we rearrange for t, because often the question is what time, how long does it take, you get this number, which happens to be the natural log of 2 divided by k. So given the right information, you can find either the constant or you can find the time. And what's nice with these, sometimes you can do it without even really having to do any math. So let's go to the next page. All right, so here we go. So now, an important thing to note is that the time it takes to get that original concentration doesn't really depend on what the starting concentration is. So when they give us some numbers, we find this to be a very easy way to find K. So let's do this first problem. A certain first-order reaction has a half-life of 20 minutes. Calculate the rate constant for the reaction. Now the key is, of course, they told us that it's first order. So we can use that equation that K equals 0.693, which happens to be the natural log of 2, 3, over the time. All right, so I'm going to plug in my time, which of course is 20 minutes. So I'm running out of room here. I'm just going to put 20 minutes. And then we'll go down here. And the answer I get when I do this problem is 0.347. You know what? Let me erase this. I'm not reading my writing very well. The answer I get is 3.47 times 10 to the negative second minutes. So it doesn't take very long. All right. So the problems can be as easy as that. But let's look at the next question. It says, get all this stuff erased here. How much time is required for this reaction to be 75% complete? So now we might actually have to think for a second. All right. So when you see a problem like this, the second one, and you think of the equation we have, they've kind of thrown a wrench into it with 75% of it complete. So what I do is I'll just go ahead and use our equation we've been using today, which is the natural log of A equals negative kt plus the natural log of A at time 0, right? And so we can just plug the numbers in. However, we've got to be aware of what this whole 75% thing tells us. Now we know K because we found K in the first problem. And without me really working it out, I'm just going to go ahead and tell you how we do it. And so the initial time, since I know this is 75% complete, what am I going to put in there? Well, hopefully you're just going to say I'd put 1, right? And then if 75% of it is gone, what's this? Hopefully you'd say 0.25, right? Or 25%. So given the t and all that, you can work it out, and you should get a number like 40 minutes, right? Now that's one way to do it with the math. Another way is, since it's first order, it kind of makes it easy for us, because if we have 100% of the stuff, right, at time 0, and then they already told us right here, they said the reaction has a half-life at 20 minutes. So at 20 minutes, right, how much is left? Well, 50, you say, 50%, right? And then after another 20 minutes, in other words, 40 minutes, what's half of 50? 25, right? So look at that. You get the same answer either way. And this works with first order quite easily. Now, if we wanted to keep going, then at 60 minutes, what would we have? We'd have 12.5 and so on. You know how it works. Okay? So that's what's kind of nice way to do those problems. You can do it the math way, or you can just kind of look at a chart this way. Either way, it'll work for you. All right? So let's go ahead and do another problem. All right? If you want, pause the video, look at the problem, see if you can do it, and then see if you get what I get. All right, so for this first one, they want us to find the rate constant, right? So I'm going to go ahead and write K equals 0.693 over T, right? And we've got 0.693. And the time is 2.3 times 10 to the 5th seconds, right? And so let me get this 3. Alright, so with my calculator I get a constant of 3.01 times 10 to the negative 6th, and it's per seconds, right? Okay, so there's that one. And then the next question says at 300 the rate constant is at. What's the half-life? Alright, so now we're doing time equals 0.693 over K, which is this number right here, right? Oops, where'd my pen go? Oops, okay. That number is right there. And when that worked, oh wait a minute, does that make any sense? Here, let me see for a sec. Yeah, that doesn't make any sense if I don't read the darn question. For all of you screaming at me and yelling and helping me out, I really appreciate it. Okay, so here, how about this number right here? Will that help? 0.693. Alright, so I get a number of 3.15 times 10 to the fifth. And this is in seconds, right? So there you go. Not too bad, right? And we're almost done. You're probably going, this is the longest podcast of my life. And this is a long podcast, but we are almost done. Okay, so let's look at this one just to show you. So you can do the same kind of problem with second order and zero order. It is most common to do half-life problems with first order, but if it happens to come up, it shouldn't bother you too much, because here you go for second order. This thing right here. I'm just showing you, this is right from the book, and this is how you take the basically the integrated rate law and convert it to this. So the half-life is 1 over the K times the concentration. So again, you're just plugging the numbers in. The thing that that does work with this, though, if you want to do the chart like I made, is if you pay attention to this line right here, each successive half-life is double the preceding one, you can kind of work it out. And we'll do some of those problems in class so you can kind of see how it works. And then if you see that it is a zero-order reaction, you can see it right here, that half-life just equals the concentration over 2 times K. And we'll practice all of these in class, and so that's the whole idea of this. Hopefully, instead of having to listen to me do this during class, you're doing this at home right now, and we'll practice these in class, and you'll get really good at it. So again, any of this didn't make sense, please feel